All right. So for those who are listening, I'm David. You guys know who I am. This is a revision workshop seminar for Algebra II. And as is my traditional method of doing these, especially for second year and beyond courses, I'm just sort of going to make it up. So bear with me. I might not have everything in a decent order. I have tried to think about it over the last day since I decided to do it, and hopefully it will all come together. So, people are mostly concerned about groups, so I thought I would talk about group stuff. Okay, so the philosophy of algebra, like in the real sense of algebra in maths, is so trying to take apart what numbers do and look at systems of objects that have operations on them, like pluses for numbers, and try and pull apart the major important features of how those operations work with numbers and see if they work somewhere else. And so we're going to take objects that we wouldn't normally consider as numbers and operations that we wouldn't normally consider as number operations and try and see if they're similar to what we would do with numbers and ordinary operations. That's the idea of algebra. And algebra is about not just numbers, but anything that you could do, anything number-like that you can do stuff to. So you're just getting into linear algebra now, which is about not just addition but multiplication as well simultaneously, and the rules that those sorts of things can live by, and what you can say just knowing the most basic rules. Okay, so once you've got a list of basic rules that you say, this is a good list of rules, what can I say just knowing those rules? So if you can do proofs of what can and can't happen using those basic rules, and then if you find something that fits those rules, then all of those theorems will apply. So if you've got something with with letters, with groups, with letters, you find something like the Rubik's Cube, and you go, oh, that's a group if I think about it in this direction, and that means all this stuff that I know about letters and numbers can apply now to the Rubik's Cube and help me solve other problems. Or not, you'd just be cool that you can say stuff. Okay, so we're interested in how things combine. In my head, when I think about algebra, I think about blobs, collections of things, which is just like a blob in my head, and you take a couple of them and you do stuff and it produces a new one. Okay, so I don't think of it like functions, so I'm just going to draw a bit like, the idea is that you've got a group which is traditionally called capital G, and it's made up of a whole lot of individual elements. And then what happens is if you take two of them, you can combine them together via the group operation and produce a different one, or possibly one of the ones that you had already. Okay, so, and this operation might be like plus or times or whatever it is. Traditionally, if you don't know what type of operation it is, we assume it's times. Because mathematicians are lazy and we want to avoid writing as many symbols as possible. And times in maths is allowed to be written without writing any symbols at all. So, yes, but that's the idea in my head, and that from any pair of points there is a path that goes to one of the other points via the plus operation. There are lots of ways of looking at groups in a pictorial way, but that's my generalized blob picture that I have in my head. So there is something, a useful other way of thinking about groups is that every element can be combined with all the others to produce the group again. So I can also think about it as suppose this one's called G. So what I can do is I can add or times G to everything else in the group, and what will happen is I will produce the group again. Okay, so I can go this one, if I times G, maybe I'll end up there. This one, if I times G, maybe I'll end up there. This one, if I times G, maybe I'll end up there. And what will happen is that if you do that to every one of the objects in there, you will end up with being able to hopefully cover everything in the group again. Not that it matters, but the idea is that you can imagine that so instead of thinking of the binary operation as something that goes from two things, you can think to say, well, for every element, there's this times G, which acts on everything else. And then this other element, there's times H, which acts on everything else. And there are yet other ways of dealing with it, but they're the two that are in my head. That I can say, well, I can take pairs of them, but I can also take a single one and sort of multiply by everything and see what I get. And then there'll be another one I can multiply it by everything and see what I get.
That's quite distinct from like cyclic groups, right? When you're raising one to a power.
Yeah, well, I'll talk about that too. Remind me if I don't mention it. I will talk about cyclic groups. Yeah, so that's a third. So I'll just say two elements combine to make a result. Okay. So this might be A, this might be B, and this would be like A plus B there.
We represent that by Cayley tables.
I don't know what you mean by that. Is that like a multiplication table?
Yeah.
Group table.
Okay, so the group table fits much more with this idea than that one. Because what you can imagine is you can say, well, I have so I'm just going to imagine this as plus. Does your lecture normally do top plus side or side plus top? Because in many groups it makes a difference, of course, because they don't know.
I think it's normally x plus y, so do the top plus the side.
Okay.
Really know?
I've never actually noticed, but I think...
Okay, it's worth checking because not all groups
Are
abelian.
Yeah.
So, but I think about this as saying, well, I'll do it side plus top actually because I'm going left to right. I think about this as, instead of having like a plus here that says what to do, I would go, well, it's all of these plus 1, it's all of these plus 2, it's all of these plus 3, it's all of these plus 4. Okay, so if I go 1 plus 1 is 2, 2 plus 2 is 3, 3 plus 3 is 4, 4 plus 1 is 1, or something like that. Okay, and then I go 1 plus 2 is 3, 2 plus 2 is 4, 3 plus 2 is 1, 4 plus 2 is 2, and so on. Okay, so you can imagine that this is the result of adding 1 to everything. And you'll see that what happens is that you make the group again. If you add 1 to everything, then you get the group back. Okay. Now, for those who are watching this, if you watch this in the future and you've never heard of groups, then I'm probably being quite confusing. But this is a review seminar, so hopefully people next year who are watching this can maybe wait until groups have been defined in the lectures. But I will get to this in a second. Okay, there is something else you can think about with groups in terms of this picture, is that you can think about just adding 1 again and again and again. Okay, so you can start and see what happens. And where do you go if you keep doing the same one over and over? And that's the idea of a cyclic group. Yeah. But I'll get to that when I'm there. Okay, so they're my pictures. Okay, so you can have this multiplication or addition table, which is apparently called Cayley table, and you can think about it. Also, you can think about it as these two combine to give that one, and that one combines to give this one. Okay, and both of them are just different ways of looking at it. They're not very different, but it helps me at least. Okay, so they're the pictures. And there are more pictures than that because most groups are the symmetries of something. Okay, so when we take an object like, say, a rectangle, and we maybe label the corners anti-clockwise like a good mathematician. Sorry?
We're supposed to go anti-clockwise.
Well, since mathematicians go anti-clockwise in other settings, I thought it seemed reasonable. So since radians are measured anti-clockwise, I do everything anti-clockwise, otherwise I'll get it wrong back there. Okay. So, I really should have done that in text, it's not very easy to see, is it? There we go. So my idea is that the operations that I can perform on this rectangle and produce the same shape again are symmetries. So I can rotate at 180, and that's a symmetry. I can flip it, that's a symmetry as well. And I can flip it that way, and that's a symmetry too. Or, in true mathematical style, I could do nothing. Okay, so the things that I could do are nothing. I could flip it this way. I could flip it that way, and I could rotate at 180. And they're the only things I can really do to keep it the same. And the idea is, with groups, is that those symmetries are the elements of my group. And if I do them one after the other, then I consider that as multiplication, in inverted commas, of my group elements. And so let's just see, if we do a 180 degree turn and then a vertical flip, so 180 degree turn, vertical flip, that's the same as what I would have done if I had just done a horizontal flip. And so I have 180 degree turn times vertical flip equals horizontal flip. Okay, and so we have this thing that says, look, I could do any number of these operations on a rectangle, and if I know about how they combine, it should come down to one of the basic ones. Okay? And that's really useful for all sorts of things, because it would be very nice to know that you didn't have to actually do all of them, you could just do this instead. Okay? Which is where it comes to Rubik's Cubes, actually. It's like, well, I know that if I did this combinations of operations, it would produce this outcome. So they work backwards to say, if I want to produce that outcome, what are the combination of operations that get there? And I can say, well, this combination would do this combination would do this combination, I would just lump them together. Okay, so that's the idea of groups. And then every shape has its own symmetries, and they don't have to be two-dimensional shapes, so that is one of the most common, but three-dimensional shapes have symmetries as well. So I could rotate it. Let me put it on the triangle so it's easier to see. I could rotate it 60 degrees, I could rotate it another 60 degrees. I could reflect it in that line. I can't do that with my real one. I was going to make one out of pipe cleaners that I could actually turn inside out, but no time. So I could reflect it in that line, and I could also rotate it vertically, right, like that, but then I would have to rotate it like that. And so there are any number of ways I could rearrange this three-dimensional shape, and so it would have a group of its own, which would be very different to one of the two-dimensional shape groups. Okay, and so this object here, which is an octahedron, would have its own group as well, as would the icosahedron. And actually, its group is called the icosahedral group. Interestingly, the icosahedron group is the same as the dodecahedron group. Kind of cool. And this is the same group as the cube. So, yes. It's to do with how their faces and edges are arranged.
Oh yeah, because if you put that inside a cube, that would actually touch each of the faces of a cube.
Yes, and also if you connect the centres of the faces of this, you get a cube. So it has the same structure. The vertices and faces of this are the faces and vertices of a cube, and the edges are the same. So this has 8 faces and 6 vertices, and how many edges that it has, and a cube has the opposite. So very cool. Gotta love the Platonic solids. Okay, so this group has a name. It's called the Klein 4 group, and it has 4 things in it. But regular shapes like pentagons and squares, they're called dihedral groups. And I don't know why dihedral, because hedral says to me that it's a solid shape, like a polyhedron. Not sure on that one. Probably to do with the fact that if you actually make a dipyramid, it's the same when you rotate. Not sure. But anyway, and this one I've just made it into a star so that later on it'll be easier to see what's going on. Because if you make a dodecagon, it's a little hard to see where one edge ends and the next one begins. So I'll just get to that later. So the whole point of groups is that they're about symmetries, but there are other kinds of symmetry that don't go with shapes. Okay, so if I have an object and I colour it in different colours, it should conceivably be possible to rearrange the colours and end up with something similar, but the other way around. Okay, and there are some formulas that are called symmetric. So there are some that have x's and y's in them, and if you can switch the x and y and still have the same formula, then that's a symmetry. Okay, so a symmetry is just a way of changing things, an operation that you perform which normally would change something, but in your instance doesn't. Okay, so something about your object doesn't change when you make that operation. Okay, and that's what a symmetry is. So in terms of a physical object like a shape, if you rub out the labels on the corners, it looks the same. Okay, the labels have moved, but the shape is the same. So if you ignore something, then it will be the same. Okay, so colour symmetries are similar to that as well. Right. So I just wanted to point out that symmetry doesn't have to be about the rotations or movements of a shape, though most groups are about that. It can be just about rearranging stuff. Okay? And that is the most fundamental and basic group that you can write on paper without having to draw pictures, which is the permutation. Right. So I better just do the definition of group before I move on. But permutations count as groups too. So you can rearrange things in a certain way, rearrange the labels on things so that the list overall is still the same list, it's just in a different order. The thing that hasn't changed is that it still has the same number of objects in the list. Okay, so we've got a definition of a group. I should just use the one that's actually from your notes, because most of them are the same, but I just want to check that I'm doing the same thing. Okay, so a group, and you have to remember definitions, and you can have any symbol here. I personally like to use an open circle, but most people use a star. So I will use that because that's what your lecturer does, but I find that circles are friendlier. So usually when you refer to a group, you don't specifically refer to the operation that you're doing. You just refer to the letter if you've already mentioned what the operation is. Okay. The point of the operation is that there are some things that naturally have multiple different operations and you have to pick one. Okay, so a group Gita, and this is a set, and this is a binary operation, meaning it takes two things and produces another one, possibly one of the same things that you had already. And you've got three rules. It's associative, meaning that it doesn't matter what order you bracket things in, it will always produce the same result. And believe me, if you live in a world where things aren't associative, it's a bitch. So, because I did that in my honours project. Bad world. There is an identity. which means that there exists an E in G with E okay, so no matter what there is an identity that when you multiply it or add it or whatever the operation is on everything in the group, you will get the same thing again. So if you go back and look at your multiplication table, the identity will be the one where this column is the same as that column, as the actual row headings. So a group is only a group if there is a column which is the same as as the column of row headings. Okay, so that's what it means. There is an element called the inverse. So for every A in G, there is so for every element there is another one that you can multiply or add or whatever it is to get the identity. That's pretty much it. When I learned about groups, there's another rule which says it's closed, which is technically, when you say binary operation, that's saying that the answers when you do star are back in G again.
Yeah.
Okay? So there's sort of like, rule number 0 is that it really is a binary operation. Okay? So some people call that closed. Okay, it really is a binary operation.
Is that what you symbolised at the top first page where you took the two elements A and B and under their composition you get A plus B?
That's right. Because what it wouldn't be a group is if when you did this it ended up somewhere else entirely. Okay, it has to be back inside G. And that's not really important for most groups that you begin looking at. It's really important for subgroups. Okay, so it really is a binary operation, which means that A star B is back in G again. Okay, that I put that rule there, A, because that's when I learned it, that's what it was. And for you guys, that was the definition of a binary operation. Okay, a binary operation is only really a binary operation if it goes back in. Otherwise, it's just like a binary function. Okay, so we know two variable functions. We saw them back in first year, and you have an x and a y, and it produces a z. And it is possible to have, two vectors and the answer to produce a number, right, with the dot product. And so that's like a binary operation, but it's not really an operation, it's just a function. It takes two vectors and produces a number as its answer. It's not really an operation unless it produces the same type of object. Okay? And when we get back to subgroups, that will come in. But I'm going to call it that, put it there, just that's secret rule 0. Okay, so it's not a group unless that operation produces things that are still in the group. Well, in the set, because you can't call it a group if it's not a group. That's the deal with groups. And the reason why this is presented so generally is that that's the whole point of algebra. Is that if you can be general and say, look, if it's just general, it's just letters and we can do all this stuff, that means that we can magically say, well, since it satisfies these, all this stuff must be true. And since this satisfies these things, all this stuff must be true for that too. Okay? And there you go. So what we saw back there with our symmetries, if I do 2 of those operations, I will still have gotten something that I could have done by doing an operation. Okay, so the group is, the set in the group is the operations that are performed on the rectangle that make it fit back in the space that it was in to begin with. And the operation is just doing them one after the other. And so if when you did them one after the other, you were able to produce something that couldn't be gotten to by doing one operation, then it wouldn't be a group, it wouldn't be closed. Okay? And I want to know that if I do 3 of them, if I do 2 and then another one, it's the same as doing 1 the first one and then the second two. Okay? And it is, because symmetries are obviously like that. Okay, if you do, well, duh, if you just do them one after the other, sure, it doesn't matter what, it doesn't matter if you do 1 and then 2, 3, or 1, 2 and then 3. It doesn't make any difference. So that's why they're our classic version of groups. Okay, and you can represent them in whatever way you like. You can represent them as letters if you want, as was done in the notes. So the classic example in the notes was Klein 4 group with I, R, V, H. I is don't do anything. R is rotate, V is vertical flip, H is horizontal flip. And you'll see that the identity reproduces the group again in the same order. But every other one, the column will reproduce the group in a different order than it was before. So, with symmetries, the identity is the don't do anything operation. So it's very much like, it's a Sherlock Holmes thing. It's if you've, how's it go? Yes, if there is nothing that can be done, do nothing. Okay, so that's the thing there. So don't do anything is a perfectly valid group object. And so that's worthwhile thinking about, that most group that if you're thinking about it in the symmetries, that don't do anything is the identity. Okay, and with inverses, it's saying, well, there must be something that you can do to get back to where you started. Okay, and with the Klein 4 group, it's fairly straightforward. You just do everything again, right? So if I flip, or then if I just flip again, I'll be back to where I started. I'll be back to not having done anything. And so the flip is its own inverse, and that's okay. It's all right for things to be their own inverses. Whereas in some other groups, like the symmetry of your pentagon, if I can find it. Rotating once that way, in order to undo that, I would have to rotate back this way, and that's the inverse. Okay, it's literally undoing. So it's not. So with the rectangle, if I rotate forwards 180, then rotating forwards 180 again will do the same thing, because forwards 180 is the same as backwards 180. But with the pentagon, rotating 180 isn't a symmetry. So that's not one of the possible things that are inside this group. So I can only do rotating how many degrees it is. 360 divided by 5, which would be 72. Rotating multiples of 72 degrees. And then you've got to remember that with some of these symmetries, of course, rotating that 72 that way is the same as rotating some number of degrees the other way. Okay, so even though they feel different to us, in terms of what they do to the pentagon, in terms of if I had labelled the corners and see which corners lined up with which corners, it would be the same thing again. And that's another theme in groups, is that there's sometimes what we consider as different to us, to the group, it's considered the same. Okay, and that comes down to some of the classic examples, which I might as well just give. So examples, symmetries, and M only has 2 humps. Symmetries, okay, which we talked about with our diagrams. Then your other classic ones are the familiar number things, which was part of the whole point of groups, is that you take, real numbers with operation plus. Okay, so if we think about it, if you add 2 real numbers, you still have a real number. Sweet. Okay. If you there is an identity and it's called 0. And there are inverses. And it's called negatives. And ta-da, it works. Okay, it's all great. And it is associative because you can add in whatever order you want. Great. The real numbers with operation times, aren't. I'll have things in, yes, yes, no. So it certainly has an identity, okay, because there's the number 1. What it doesn't have is inverses. Like pretty much everything has an inverse except 0. So if it's only broken once, then it's not a group. Okay, and that's one of the ideas of maths. It doesn't have to work. If it works for everything, but there's one thing it doesn't work for, then it's not the type of object we're interested in. Okay, so 0 doesn't have an inverse. Okay, there is nothing I can multiply 0 by to get 1, which is the identity. And so what you do is you remove 0 and suddenly it works, which is what your electricals are star, I think. All right. A classic thing that is not a group because of rule number 0 is the natural numbers with plus. It's not a group because plus doesn't count as a proper binary operation with the natural numbers. Well, plus does, but there's no inverses. So, that's not either. Okay. Subtraction isn't associative anyway, but when you subtract 2 natural numbers, you don't necessarily get a natural number. So it's not even closed, and that's rule number 0. So technically subtraction doesn't even count as a binary operation on the natural numbers, which is where I find it hard to understand all it's a binary operation up in the real numbers. Okay, so it's not closed, but it's also not associative, because A minus B is not the same as that. Okay, cool. But, e.g. 3 minus 4 is not in the natural numbers. Okay, so you need to have a good handle on the 5 families of number and what happens to them when you do the basic operations on them, so that you can use them as your base examples of things that behave like numbers. You need to have a good imagination for the symmetries of shapes, so that you can use them as a basis for symmetry groups. And then the final thing that we need to have examples of... stop. There is another kind of group. These ones are infinite, right? I've got infinitely many numbers in them. There's finite groups, which are really the basic type of group. Something like Z5, which means 1, 2, I missed 2 because I said it. Those 5 numbers, okay, so 1, 2, 3, 4 and 0, under plus, where it's mod 5. Okay, so that means that you have to treat things as if they were, it was on a clock. Okay, and actually these are symmetry groups too, it's just the rotations of a whatever gone. Okay, so these are the same as rotations of a pentagon. So you can think of your Z whatevers as rotations of a something gone. So if I does that go through? Oh, good. Okay, so I can think of not rotating as 0, rotating once anti-clockwise as 1, rotating twice anti-clockwise as 2, and this as 3, and this as 4. So if I have 2 plus 3, I have 2 plus 3, which is the same as not rotating at all. So 2 plus 3 is 0. Okay? But 3 plus 3, 1, 2, 3, and another 1, 2, 3, that's the same as rotating once. So 3 plus 3 is 1. Okay, and I think about it with a clock. Okay, you get a clock, 2 o'clock, 10 o'clock plus 4 hours, it's 2 o'clock. 10 plus 4 is 2. Alright? Feeling good?
Yeah.
Okay. So you can also think of, remember, my other idea of taking a group and adding something to everything harks back to my idea of how vectors add. The first vector is a place and the second vector is a distance to go. The same deal, you can say that 3 plus 3 is, take the number, I've labelled it the wrong way around, sorry guys. You put the 1 there. So 3 plus 4 on the hexagon, 3 is a place to start. 1, 2, 3, 4. 3 plus 4 is 1. That's 0 there. Okay? So that's the idea. Feeling alright?
Bring the shapes. Yeah.
So Z5 is actually not really a list so much as a circle. Once you go past here, you end up back here again. Okay, Pac-Man addition. You go out one side, you come in the other. Okay. Did it again.
Now that 1 plus 2 and blah blah and n minus 1 diagram makes sense.
Is there a diagram, is there?
Oh, she drew basically the same thing, but then 0, 1, 2.
The equivalence classes.
Yeah, and then n minus 1.
Yeah.
Like behind ZN.
Yeah.
Yeah, so these are, technically it's not really the numbers from 0 to 4. In the full definition of this, 0 is really all of the numbers 0, 5, 10. It's all the multiples of 5. And 1 is really all the numbers that are 1 more than multiple of 5. But really, no one thinks about it that way. What they really think about it as is the numbers 0, 1, 2, 3, 4 arranged in a circle.
Yeah, because that makes more sense.
Okay? But what we're saying is that, look, 6 is the same as 1. Because going 6 from here is the same as going 1. Okay, so it's that idea that what I consider as different, the group doesn't. Okay, I consider it feels different to me to do 6 around this circle, but to the group it's the same. Okay, because going 1 gets me here is the same as going 6 because it gets me to the same spot. Okay, similar to vectors, remember? Exactly, displacement in physics.
The path is path independent.
Path independent. So displacement in physics doesn't matter the path you took to get from here to here. The displacement is just that journey. Okay, we go.
So it's where you end up that counts.
Oh dear.
I think you might do something.
Just knocked everyone outside space.
The location was in the subject, not in the
No.
Oh, did I not put the location in the email?
No, it was in the subject. It took me like
Frail.
10 minutes to figure
Sorry
it out.
guys. I usually put everything in the subject and then everything in the email, so if you're just looking for the email then you can just read the subject line.
No worries, it was good.
But I forgot to put it in
I
the...
was more concerned about everyone thinking that I was late.
Well, I was disparaging you. I was saying nearly so financially got this.
No, I was here.
We didn't record any of that conversation, I don't think. So, okay. And that's your classic Z whatever. Okay? So Z12 is the geometry, is the numbers on a clock, except that 12 is 0. Okay, but there's nothing to stop me calling 0, 5 or 12 or whatever I wanted. It's just that 0 feels better as an identity. Adding 0 means doing nothing. Okay. Right. Cool. And most of these Z whatevers are not groups under multiplication because they've got a 0. Okay? But if I did just the numbers 1, 2, 3, 4 under multiplication mod 5, totally a group. Okay? And that will only be true if the number is prime. So, okay. Yes, ZP for P prime without the 0 under multiplication is a group.
Sorry, it's not prime, because like if you've got Z6 and do 2 multiplied by 3, you get 6, which is 0. It's not in a group.
So that's your 2n plus 1, because it's an even number, rather than just...
It doesn't have to be even, it just has to be, not prime.
Composite.
So the idea is if it's a composite number, you can get 2 numbers to multiply to produce 0. Okay, with 12, for example, 3 times 4 is 12, but 12 is 0, and 0 wasn't part of this set, and so it's not closed. Okay, so it's not technically a binary operation.
Can I just ask, right, you're saying that it's Z5 and removing 0 and then still doing mod 5 addition on it. So with that
No.
Or you weren't saying
Addition mod 5, if you remove 0 and do addition mod 5, it's totally not a group anymore.
Yeah.
If you remove 0 and do multiplication mod 5,
multiplication
yes.
mod 5.
Yeah.
Okay.
Okay.
I was going to say, yeah, if you took the 0 out of that pentagon picture there and tried to do addition mod 5, it would
Then you'd fall into the hole.
Yeah.
So way back in Math 1A and B, where I talked about subspaces, things with holes aren't subspaces, or things with holes aren't groups either. Unless, of course, technically you can't achieve something in the hole. So if you remove this and do addition, then you can fall into the hole by doing 4 plus 1. Fall into the hole by doing 4 plus 1. But if you did it with multiplication, you can't fall into that hole. Okay, because 1 times 3 can't be 5. There's no way of making a multiple of 5 out of those numbers by multiplication. But if it was on a clock with 12, sure, I could multiply and fall into the hole. So that's a nice way of thinking about it if you want a picture. Okay, and that's why it's so important to think about closure as secret rule 0. Because sometimes when you remove an element, so if you've removed an element, you've created a hole, which means that it's possible to not be closed anymore. So it's not a group because technically it's not a binary operation. So in your, if you were going to have an exam question and it was not a group because it wasn't closed, you should say the operation isn't closed, so it's not a binary operation, because that's how it's said in your notes. Okay. It's probably okay just to say the operation is not closed, but so we've but I don't I just don't want to get you lose a mark or something. Okay, so there are classic groups, but there is one more kind of group which goes with symmetries of things where we're not having physical shapes and rotating, because even Z5 is really just rotating anyway. Like, it's not about the symmetries of shapes, even with restrictions. So we had a restriction that says symmetries of a pentagon, but you're only allowed to rotate. Okay, so we want things where the symmetry can be anything. We're allowed to just rearrange stuff and the picture looks the same, and we don't have to rearrange in a physical sense of picking something up. And those are permutations. So and that really has a section all of its own. But yes, permutations form a group. So now the thing is that all finite groups can be thought of as sets of permutations. Okay? No matter what kind of group it is, if it's only got finitely many objects in it, you can repitch it as a permutation if you want to, which is why permutations are so important to group theory. Okay, because it gives us a classic a way of writing it down on paper without having to draw pictures. So I'm going to give you the example back here with my rectangle. Okay, so with my Now this is not a full set of permutations, but I just want to point out that it is permutations. My Klein 4 group with a rectangle, if I flip it horizontally, then let's just see what's happened. What used to be in position 1 is now a 4. What used to be in position 4 is now a 1. So now this is what it looks like. And so we have that 1 became 4, 2 became 1, 3, whoop, that's a 2. I did it again. See, if I had them labelled with letters, I would probably be better because I'm used to doing that cyclically. So 1 became a 4, 2 became a 3, 3 became a 2, and 4 became a 1. So what this flip did to the numbers is it created a function. We had numbers going in and results coming out. Okay? And every one of those operations can be thought of as a function of the numbers 1, 2, 3, 4 that produces a result. Okay? And I rearrange them in some way. Alright? And so that's the idea of a permutation to a mathematician. It's a function of the numbers 1 to something. Okay, so what we had is a function from the set 1, 2, 3, 4 to the set 1, 2, 3, 4. Okay, and the rule which says what the function is, there is no formula for this function. It is just, here is the inputs, here is the outputs. Traditional big version, I don't know what the name for it is, but traditional big version of permutation notation is to write the 1, 2, 3, 4 at the top and what they become at the bottom. Okay, so you have inputs 1, 2, 3, 4, outputs 4, 3. Okay?
Yeah.
And that's your array version of your permutation. Okay, the top line is always 1, 2, 3, whatever, and the bottom line is what they become afterwards. Okay, so when you perform this on the corners of the rectangle, you produce the rotation, the horizontal flip. But when you perform that on the letters A, B, C, D, you will get DCBA. Okay, so you're saying whatever is in position 1, the answer is now whatever used to be in position 4. Okay, and so it's a way of rearranging things, and I do find it useful to think about it as letters as well. So to say, well, if I perform this, permutation upon this, the position 1 will become whatever used to be in position 4, and position 2 will become whatever used to be in position 3. And position 3 will become whatever used to be in position 2, and position 4 will become whatever used to be in position 1. Okay, it's telling you what to put in each position based on what was there before. So if I do this permutation again, I'll get back to where I was. Okay, so I can say, all right, position 1 is whatever used to be in position 4, which is A. Position 2 is whatever used to be in position 3, which is B. Position 3 is whatever used to be in position 2, which was C, and position 4 is whatever used to be in position 1, which is D, and I get back to where I started. Yay! Okay, so this permutation has order 2 because it takes 2 to get back to where I was. Okay. There is a shorter version. I mean, if you look at this, technically you could imagine that you wouldn't need that top line. That's not actually necessary at all, because you know it's already always 1, 2, 3, 4, but that's the traditional way of doing it. Because you can imagine if we were doing our permutation on ABCD, you would put ABCD in whatever it was. Okay. So there is another way of talking about these, which is cycle notation, which is a picture of where everything goes if you keep doing it over and over. Okay, so you talk about what goes to what, and you just say, well, all right, something goes to something, and then that thing goes to the next thing, and 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 you keep going until you get back to the beginning. Okay, and that was the picture that I was going to draw when I got to that. Okay, so We can do this in cycle notation as well. Okay, so the idea is you always start at 1 because you've got to have a system. So it doesn't matter which one you start at, but starting at 1 seems reasonable. So start at 1 and you say, what does 1 become? Well, 1 becomes 4. And then start at 4, what does 4 become? Well, 4 becomes 1. And so 4 goes back to 1, so I close it off because I'm back to where I started. And then I take the next number that I haven't yet seen, so I've got 1 and 4, so maybe 2. Now I start at 2, where does 2 go? 2 becomes 3. And I start at 3, where does 3 go? 3 becomes 2, which is back to where I started in that cycle. And that's how to make cycle notation from table notation. You can go back the other way. It's actually quite straightforward. I'll just do an example. Cycle to table.
Can I just ask you something?
Yeah.
Right. You know how you said earlier how that permutation has order 2 because
when you do it twice, you come back to the
twice
start.
you get to the identity.
Yeah.
Is it also order 2 because it's the product of 2
transpositions?
Yes.
That is also true.
Yeah.
But in the pure sense of the definition of order, order is about doing it twice.
Okay.
But it is also true, I mean, part of the power of cycle notation is to be able to just look at it and know without having to actually do it over and over to see what happens. And we'll talk about that. Thank you. So to go from cycle to table, so suppose we've got a permutation of 7 things. One, 2, 3, 4, 5, 6. Okay. I need to specify how many there are, because if something's missing, it just means that the permutation doesn't do anything to it. Okay, so this is a... Let me put it in. Let's suppose this is a permutation of 8 things. Okay? The fact that 8 isn't represented says that it doesn't do anything to 8. Okay? So let's see, 1, 2, 3, 4, 5, 6, 7, 8. So let's see, 1 goes to 2, and then if we go to where 2 is, 2 cycles back round again and comes to 1. So it's the same as our Z5, you've got to think of it as a circle. 3 goes to 7, alright, 4 cycles back round and goes to 3. I'm just going along this list. 5, where does 5 go? 5 cycles back around and goes to 6. 6 goes forward to 5. 7 apparently goes to 4. And 8 isn't represented, so it stays the same. Okay, so that's how to get them back to each other. Okay, that's the idea of cycles and the 2 different notations for permutations. That's how they relate to each other. Cycle notation is just a really shorthand version that says, well, if I start at 1, where do I end up? And what we've actually done here is we've said if I keep doing this permutation over and over, what will happen to, say, 3? If I kept doing this permutation over and over, the 3 would become a 7, then it would become a 4, and then it would become a 3 again, then it would become a 2, and then it would become a 4. Okay, so saying that these things will cycle around that way if I keep doing this permutation over and over again. Whereas this is harder to follow in this one. You can say, well, 1 becomes 2, so 3 becomes 7, and then 7 becomes 4, and then 4 becomes 3, and you can't see that straight up. So the cycle notation is better because it doesn't just give you the information about what each thing becomes, it gives you the long-term information if you keep doing the permutation over and over. Whereas this is only giving you one step, whereas this is giving you all steps. Okay, so they're a group, right? Permutations are a group. If you do one permutation and then another permutation, you'll get, as a result, a different permutation that you could have gone direct. Same as with displacement, do one arrow and then another arrow, you could have gone direct, and that would be a different arrow. So it's the same deal, and somehow you have to figure out what the result is. Okay. So So suppose we've got the traditionally used Greek letters for these things. So sigma's that, tor is maybe something like that. Okay, so sigma is a permutation. It will take a list of numbers 1, 2, 3, 4, 5, 6 and produce a new list of numbers. Tor is a permutation as well. It will take a list of numbers and it will produce a new list. If I do one after the other, I will get another different list, and I want to know what that is. So I'm going to do it in cycle notation. So sigma. Okay. So remember, sigma doesn't just act on a list. You think of it in order to make this work. In order to make the system work, you actually have to think of sigma as a function. So it's actually saying that sigma takes an input and produces an output. Okay? So you can imagine, this is what we're thinking, that sigma of some number, sigma of 1 as a function comes out to 2. Sigma of 2 comes out to 1. Sigma of 3 comes out to 6, etc. Okay? It's a function. And similarly with tor, or tau, if you like. So sigma tor, we imagine it as a function, which means that the object that it's working on is here. So we imagine sigma tor. We're going to find sigma tor. Well, let's imagine sigma tor of a number, shouldn't use n, of a number is sigma of tor of the number. Okay, so that's telling me that if I do a number, I need to do tor first. Sorry?
That's why we go from right to left.
That is exactly why we go from right to left. I need to do tor first and then sigma on the numbers.
Yeah, I found this really confusing.
I was just doing it.
So much.
But we're thinking of them as functions.
Let's stack the two permutation notations and then swap the middle rows as in the columns, then make it like a rock of rain that comes down. That's the way I got it.
Whereas if I'm going to do this in cycle notation, I'm actually thinking of it as sigma. So sigma tor is sigma and tor. Okay, and so remember, this is sigma, this is tor, and then it's acting upon a number which is over here, because it's sigma of tor of number. So there is my number which is here. So this is my input, and it moves this way to produce an output. Okay? So let's see, if we put the input 1 in, it's become a 6. By the time it's passed through this cycle, the 1 has become a 6, because that's what this cycle says. So the 1 has become a 6, the 6 becomes a 5 in this cycle, and this cycle doesn't change 5. So by the time we go between here and here, the 1 has become a 5. Now let's look at the 5. Where does the 5 go? I work my way along here, the 5 has become a 2. The 2 doesn't change in that cycle because it doesn't mention 2, and the 2 cycles back and becomes a 1. So by the time the 2 has passed through all of them, it has become a 1. The 5 has become a 2, and then it's become a 1. So 5 becomes 1, I can close it off. Now the next number I haven't used yet is a 2. Let's see, 2 becomes a 1, and then it becomes a 2. So in fact 2 doesn't change at all. It becomes a 1 and then it goes back to a 2 again. So when I do my final cycle notation, I'll completely leave the 2 out. But I am allowed to put it there like that if I want. 3 isn't changed by that bit. It becomes a 6 here, and then that doesn't change to 6. So 3 becomes 6. 6 becomes a 4. 4 isn't changed, 4 isn't changed, so 6 becomes a 4. 4 becomes a 5, and then the 5 becomes a 3, so I can close that off, because 4 has now become a 3. And then what have we got? 1, 2, 3, 4. I've got all of the numbers now. Okay, so there's none left, so that's the same as 1, 5, 3, 6, 4. And tau sigma would be something else again, because I would have to put it in the opposite order and things would happen in a different order, and so the permutations would be different. Yes, it took me many moons to figure that out. So I'm pretty sure my lecturer, whenever I saw this, was actually quite explicit about how to go about that. The other picture that I have in my head is actually I do physically imagine the numbers moving. I actually say, well, it was a 1 here. By the time it ended up here, it became a 6. By the time this ended up here, it became a 5, and now it's still a 5. So 1 goes to 5.
That was very helpful.
I ended up like doing it in arrays, like, and writing them all out long and painfully, like f of g of x or whatever. So,
Yeah.
you know, this goes to this, goes to this. Like when you taught us composition of functions,
Yeah.
just heaps long arrays.
So yeah, I'm just doing this in my head really. But the point of cycle notation is so that it's possible to do all this without the extra work.
Yeah.
And so
That just makes sense. And also the order in which you're like, once you close off a group, so you sort of just arbitrarily start at 1 and then go.
Yeah, we
we've
have
done 1 and 5 in that group. Now we'll go to 2 because that's the next most obvious thing to go to.
So for those who can't hear that,
What does it become?
yeah, for those who can't hear that, you have to start somewhere. So you start at 1 and then you go, well, we haven't. But what's the next number we haven't seen? And it's good to have a system. I mean, you can do it in whatever order you want, but it's better to have a system because then you don't miss them. And I would even be, if I was being particularly worried about it, I would write the numbers 1, 2, 3, 4, 5, 6 and cross them off as I dealt with them, so that I didn't lose track of anything. Because it's really important to do that if you know that your permutation between them haven't covered all of the numbers. You can say, well, I've covered 1, 2, 3, 4, 5. Now 6 isn't mentioned anywhere, so it's fixed. Yeah. So.
And it's identical, right? If you had to raise a cycle to a power, right? You just do this exactly the same way.
That's right. So if I had to do, right, so let's do that. So powers is done exactly the same way as we think of powers. If I had to do like sigma cubed, then that would be the same as sigma, sigma, sigma. And so you could actually just do exactly the same thing and work your way from the left and see what you get. You know, right, 1 becomes a 2, and then it becomes a 1, and then it's back to a 2. 2 becomes a 1, and then a 2, and then a 1. 3 becomes a 6, and then a 5, and then a 3. 4 isn't even changed by any of these. 5 becomes a 3, and then a 6, and then a 5. And 6 becomes a 5, and then a 3, and then a 6. So sigma cubed is 1, 2. Yeah?
Say you find sigma squared first, you can just say that sigma cubed is sigma times by sigma squared, and it doesn't matter if you do sigma first or sigma squared.
No.
Okay.
Okay, so you could have, if you wanted to, figured out what sigma squared was first, which would be 7, 3, 1, which would be that. Yep, divide by sigma, which is that, I think. Could be wrong. And then you could say, well, sigma cubed is sigma squared times sigma.
Oh, it is.
Like that. Or you could do it the other way around. So, or sigma cubed is sigma times sigma squared. Sorry. Yeah.
So it's quite different to a composition of different ones, like when you do sigma to or sigma.
I pressed something again. Damn.
Pen saver.
Hey,
It's a pen saver.
yeah.
Think of how much ink is there.
Okay, so, and it doesn't matter which, you'll get the same answer either way. Because group operations are associative. But also, commutative means that you can do it literally, you can switch the order, and everything commutes with all its own powers. So a cyclic group is automatically abelian, in case you're interested. Okay, so there is something slightly more in the power of cycles, which is that there are a couple of rules you can use before you just use that. So we've got a standard rule, we can always figure it out by working from the left and seeing what happens to our things. But we can also know that you can flip them round if they don't involve the same numbers. So, pardon me, sorry. I could have said that.
Never seen this side of you before, Brandon.
Well, see, that doesn't involve the same numbers as that, so I could just as easily go 1, 2, 1, 2, 1, 2. Like that, if I wanted. Because you can rearrange them as long, you can flip them round as long as they don't involve the same numbers. So you can't rearrange them however you want, but I can move this to the front of that.
And that's the product of disjoint cycles.
That's right. So product of disjoint cycles, if they don't involve the same numbers, you can flip them around the other way. And 1, 2, 1, 2, 1, 2 is, well, this flips the 1 and the 2, and this flips them back again, and this flips them again. And so 1, 2, 1, 2, 1. So 2 of the same transposition is the identity.
Oh, this is a way to cheat through it pretty much, because the next one's a order.
So this is 1, 2, 5.
Yeah. So this is
the
the
identity from that.
That's right. This permutation is order 3. It's got 3 numbers in it, and by the time you've done it 3 times, you'll end up back at the beginning. Okay? So that's sort of the way that's using a couple of things. So we have a couple of rules that say a cycle of order whatever, which has a certain number of numbers in it, if I do it to that power, it will give me the identity.
So that's how you justify that move.
Sorry, what's that?
In an exam.
Yep.
Justify it with that comment.
Mm-hmm.
Without
So-
actually having another one out.
So you can have that. I could do it like that if I want. Just 1 if you want is the identity permutation. And so you can have that cycle R to power R is the identity. Okay?
Yeah.
Okay? So the thing is, there's no point learning facts like that somewhere in the lectures if you're not going to use them. Right? It's like learning the facts that, you know, the road rules, yeah. But I mean, a whole lot of other things just about numbers where you go, well, I know if I multiply by 5, it's the same as timesing by 10 dividing by 2. So, you know, dividing by 5 is the same as timesing by 2 and dividing by 10. Like, no point knowing that fact unless you're going to use it in times of need. So, there's no point knowing that you can flip disjoint cycles if you're not going to use it to put cycles together so that you can use this fact of cycles to the power that they are is the identity. So the other trick is that you can, if you have a single cycle to a power, you know that what that is doing that multiple times. So if I did Tor, for example, cubed, and Tor was back here, was 52164. Well, I know there's 3 of them in a row, right? So let's see. 1 goes, so 3 steps. Goes to 6, goes to 4, then it goes to 5. 5 goes to 2, to 1, and then to 6. 6 goes to 4, to 5, and then to 2. 2 goes 1 to 6, and then to 4. 4 goes 5, 2, and then to 1, and I close it off.
didn't realise this was a comedy show.
Oh.
That's so easy. So easy. So you're doing the power, you're doing how many jumps?
That's right.
So you just like.
So the power represents how many jumps?
So if you do it once, it's only one jump, right? So, one goes to 6.
Yeah.
So if you do it 3 times, you do 3 jumps. Which is why, if the length, if I did this in power of 5, it would be the identity because everything would go 5 jumps and come back where it was.
So towards the power of 5
Would be the identity. Yeah.
Because you jump 5 times, you come to the same place.
Which is analogous with the turning of the clock.
Exactly. Okay. So the whole point of cyclic notation is to know these things. Okay.
You can appreciate the fact that you've written it out 1,000 times.
Yeah.
That's good.
That's right. You must walk the steps before you enter the temple.
Okay. So that's the whole idea of cyclic notation. Right. So you can actually know the order of a permutation as in the number of steps it'll need to get back to the beginning by investigating its cycles. So sigma, the order of sigma, which was 1, 2, 3, 5, 6, was it?
Yeah.
Well, if I kept doing this over and over, right, it'd actually be, this to a power and this to a power. I know that every second power of this is the identity, and every third power of this is the identity, so I'm going to need to go 6 to get to the identity. Okay? Okay, so it's the lowest common multiple of the lengths of the cycles, basically. But that's why it's to do with the jumping. Yeah. Okay. Right. Now, permutations form a group, but usually what you do from permutations is you actually just take a smaller collection of them and make a group out of those. Okay, so with your rectangle, there's only 4 of the possible 24 permutations of 4 things, and with your square, there's only like 8 of the possible 24 permutations. And so you, most of the time, when you're looking at groups that actually act on other objects, and you're not raw permutations, you're only having some of them, which is where the concept of a subgroup comes from. Okay, you just want some of them, and together, in their own right, they form a group. Okay? So, right.
So like SN are the big ones, and
so the set of all permutations of n things is the symmetric group of order. Is that order? Anyway, the symmetric group on n elements. And it's called the symmetric group because it encodes all possible symmetries. Okay? So most physical objects have less than this many symmetries, but this encodes all possible symmetries that any object could possibly have if it has n corners. Okay, so even if you're allowing things that you don't traditionally allow. Okay, so no matter what you could possibly do to an object, even if you're allowed to tear it and glue it back together or whatever, it must be among this list. Because the corners are just going to end up on one of the other corners. So it's just a rearrangement of the numbers. Okay, so that's a set of all permutations of n things, and it has size n factorial. The size of Sn, also known as the order of a group. But then all other groups can be made out of those, and so you take a smaller collection of them which is closed, then be a subgroup. So the idea is that, the Klein 4 group, my symmetries of my rectangle, which was the identity
5, 6.
1, 4, 2, 3. That's the horizontal flip. 1, 2, 3, 4. That's the vertical flip. And 1, 3,
2, 4.
4, 2, isn't it? Just a second. So 1 became 3, 3 became, yeah. Okay. So you'll see they're all made of 2 transpositions.
Which is right, because they're all two.
What about we don't talk about the reflection then?
That was my flip, my horizontal. This is the horizontal reflection, that's the vertical reflection, that's the 180 degree rotation.
Oh, right, yeah,
So this is my horizontal, this is my vertical.
No.
Because it won't, because it's a non-square rectangle. Yeah, so a 90 degree rotation doesn't put it back where it is, and so it's not, as you're right, it's not part of the group. Okay. Cool. Whereas with a square, the 90 degree rotation does count. Okay, so a non-square rectangle. Okay, and it's made of permutations, but if I do any of those permutations on themselves or on each other, I just get one of these again. So it's completely closed. Okay, there's nothing I can do if I just maintain these and multiply them by each other. I'll never get any of the other permutations. So it's self-contained. So it's a group. If I didn't know that the other permutations existed, I would never know if all I had was this. It's completely self-contained, and that's the idea of a subgroup. Okay, it's self-contained, and so that idea of closure is really important. But you want closure in all of the things that are important. The identity has to be in it. Okay, if it doesn't have the identity, it doesn't have an identity. Okay, so it's not a group. The group operation has to be closed. Right? No matter what you do, if you multiply the things together or add or whatever the operation is, you have to only be able to produce things that are still inside this set. And inverses have to be closed. Okay, you need to be if you find the inverse of any of them, it has to be still inside the set. So all of the things that we are interested in for groups have to be closed, self-contained. So that's the idea of a subgroup. A subgroup H of G is a group under the same operation, basically. It's a subset that is also a group. Technically, G is a subgroup of itself, but to say a proper subgroup would be that it's not equal to G. And the identity all by itself is a perfectly good subgroup, and that's the trivial subgroup. I think G is trivial as well. So it's a group under the same operation, which basically means that everything's closed. You know, it's self-contained. The point I was trying to make about the symmetries of the rectangle is that from the beginning, your very first examples of groups were actually already subgroups of something else. Okay, so most groups that we could think of as examples are already subgroups of bigger groups. So it's not an alien idea. Those rectangles permutations, well, they're already just some of the possible permutations it could be if it wasn't a rectangle, if it was just a random collection of numbers. Okay, the fact that it's a rectangle restricts it to just these ones. So yeah, it's not an alien idea. But to tell if something's a subgroup can sometimes be a bit tricky because it has to be self-contained for every possibility. And so there's this test that I learned. I don't know if you learned this test. I think you learned 2 separate things. But if for every element that's in it, A, B inverse is in it, like there's a test that says if for all AB in the subgroup, then AB inverse is in the subgroup, then it's a subgroup. I don't know if that's the one that you
Like the
learned.
inverse of AB together or A times
A times the inverse of B.
I think we've just tab, if AB exists in H, then AB exists in H, and if A exists in H, A inverse exists in H, which is just the long way of saying that, really.
Yeah, this covers both of those. Yeah, but if you haven't been told that one, so it's true. But yeah, you need it to be closed under multiplication or whatever the operation is, and closed under inversion, and that will cover the identity anyway. Because if it's closed under inversion, then the inverse will be there, and then times by its inverse will produce the identity. So you don't technically need to check the identity, but it is worth checking. You say, if the identity is not there, it can't possibly be a subgroup. Okay.
Is there a good logical order to do a group test?
Look, I don't know. If they're numbered already, like Z whatever, you just start at the bottom. I would do all the inverses first. So I would, if I was going to check, I would check the identity, because you're going to have to check if something's there or not. If the identity is not there, then you can stop, right? Not a subgroup. And then if the identity is there, then you want to check the inverses, because if your group has like 5 elements in it, subgroup or proposed subgroup has 5 elements in it, you only need to find 5 new elements, right? And then multiplication, if there's 5 elements and there's 25 possible multiplications, and so that's the hardest one to check. So I would then multiplication. I would check though in that order if I was going to find if it was a subgroup, because if it broke here, you haven't done much work, and you know it's not. If it broke here, you haven't done all that much work, and you know it's not. And so it's an economy of the amount of work it takes to achieve.
We had one of them in our mid-semester test, and it was a subgroup of, say, 10, I think, it was 1, 3, 7, and 9. And so you had to show it with multiplication, under multiplication, right? And so the most economic way I think to do that one was to show the group table, right? Because is that satisfactory? It's like,
well, this is checking if something's a subgroup.
Oh, okay, sorry.
Not checking it's a group at all, but that it's a subgroup. But
well, they told us it was, yes, in the question.
Yeah.
Or was it? What did they say? Prove that it is.
So almost all examples of things that are supposed to be groups, almost all examples of things that are supposed to be groups are really subgroups of something if they are. So you do multiplication mod 10, you've got these numbers. Well, if it is a group, it's going to be a subgroup of Z10 star, right? So it's actually useful to think in terms of subgroups. And it's the reason why something is not a subgroup is usually because it's not closed. Because the thing is that, multiplication mod 10 is perfectly associative and it has an identity, right? So, though interestingly, the even numbers under multiplication of mod 10 actually are a group. Sorry, a field. So the non-zero even numbers under multiplication are a group, but it's not actually a subgroup of Z10. So.
This is not zero.
Sorry?
This is no zero.
No, it is a subgroup of Z10 star. You're right, it's a subgroup of Z10 star. Yep. Yes. Okay, so I can keep going for a bit. Not quite sure when my time is going to run out. Okay, so that's cool. Now here's where it gets a bit zen. So we've got groups, we've got all these things multiplying or adding or whatever it is that they do and producing new things. We've been able to create cycles. The only thing I haven't mentioned yet is that you can create a subgroup just from one element by doing it over and over and over. Okay, so okay, the subgroup generated by an element G is denoted by that and is the identity and G squared, and however many powers it takes to get back to the identity, if indeed it does it all. It might not get back to the identity ever, because it might be something like 1 in Z under plus. So as an example, if you're in Z, now 2 in Z under plus, you've got the identity which is 0. You've got 2. And the negative powers too. You have to be able to do the inverses too. So we'll have 2, 4, 6, and so on forever, and then -2, -4, and so on forever. Okay, so it's all the even numbers. Okay, but mostly we don't care about those. They're actually much less interesting. And the name of this is 2Z, by the way, in case you've, that's 2 times everything in Z. That's bad. Okay, so cyclic groups in infinite set groups, cyclic subgroups of infinite groups are really not that easy.
Yeah.
But they tend to have that sort of structure. They go on forever.
There's no power you can raise 2 to, so you get back to 0.
Yeah. But of course, -1 in Z under Z star under times, well, it's a perfectly good finite cyclic group. So, e.g. Okay, so Z star under times as a group, we've got the identity which is 1 and -1, and -1 squared is 1, and -1 cubed is -1, and so we end up with just those two. And -1 inverse is -1, and so there's just 2 elements in that. Okay, so we can do the powers as often as we like, and we end up with just those 2, because we do the power and then we do the power again, and just cycles round and round. Okay, and this is what must happen in a finite group. So in my head, I actually don't. The infinite ones freak me out. I like finite groups, and so you can have your picture, and you have G, and then you times. You have the identity, right? And then you times by G, and you get to G, and then you times by G, and you get to G squared, and then you times by G, and you get G cubed, and then you times by G, and you end up back at the identity again. And so you get this little cycle, like that. And that is your cyclic group. Okay? And that's the picture I have in my head. That you just keep doing it over and over and over, and you end up back where you started. And that's cool. And that means that every group, every element has a group that it's part of, and that group has an order, which is the number of elements that are in it, and we declare that to be the order of the element. Okay, so the size of the subgroup generated by B is the order of G. So when we talk about the order of a permutation, that means the number of elements in its subgroup, which means the number of times you can do it to get back to the identity, which is the same thing, because like the subgroup generated by the thing is all the things you have to do before you get back to the identity. Okay, so it's also equal to
the order of lowercase g in capital G.
Yeah.
The group order we call it. Is that right? I just got confused on that one.
Yeah, so the order of an element living inside a bigger group
Yeah.
is the number of times you have to do it before you get back to the identity.
Yeah.
And if you can never get back to the identity, then it's got infinite order.
Yeah.
Well, yeah, something like that. Okay, so in a finite group, every element has an order, and every subgroup has an order. And there's this big theorem called Lagrange's theorem that says that the size of a subgroup has to divide the size of the group. And the size of an element, by analogy, has to divide the size of the group. So if you think on a clock, the order of 6 is 2. You do 6 twice, you get back to 0. Okay, the order of 3 is 4, because you do 3 4 times, you get back to 0. But those numbers divide the size of the group. And they have to, because it's to do with how many times you're going around the circle. Okay, so, but the proof that they have to has to do with cosets, which is a whole separate thing. Okay, but that's where it gets really zen. Coset. So we've got this theorem. The order of a subgroup, if H is a subgroup of G, then the order of the subgroup divides the order of G. Not to say that every possible number that divides G will give you a subgroup. That's not true. But if there is a subgroup that has a number for its order, it will divide the number that is the order of G. If G is already a cyclic group, meaning that you can make it out of a single element this way, then there will be exactly one subgroup of every possible order that divides the order of G. So I don't know if this is a theorem in your notes, is it?
Yeah.
So this is Lagrange's. There's another theorem that says, if G is cyclic, i.e. G is the generated by something, then for every number dividing the size of G, there is not one, but there is a subgroup of that size.
And that's why every prime numbered subgroup is cyclic.
Yeah, it has to be, because nothing divides it.
Yeah.
So, yeah. So if a group has prime order, it can't have any subgroups other than just the identity. Because those would have to divide the size of the group, and the size of the group is prime. And that means that any element, the group that it generates, has to be the whole group, because it can't generate anything smaller, because that number would have to divide the size of the group. Okay? So if it wrapped around halfway, then that size would have to divide the whole size, and it can't because it's a prime number. So yes, all groups of prime order are the same. Now, I'm not going to have time to talk about cosets, but maybe I'll do another one at some point near the exam. I do have one more thing, so I'm going to talk about isomorphism. So this is where there are two things that make group theory sort of zen. And they are isomorphism and cosets. And cosets gets very zen. It's all self-referential. And I can talk about that another day, but I have other things to do today. But I can talk about isomorphism. So this is all well and good, right? That groups, we've got groups, we can make groups out of permutations, we can make them out of symmetries, we can make them out of numbers. There are three classic ways of making groups. We can make them out of matrices as well, we can make them out of functions. Technically permutations are just a kind of function anyway. So they're the ways that we can make groups. So, ways... we can make them out of numbers, we can make them out of symmetries. That's the classic, and that's what groups are for in terms of the applications of them in the rest of the world. We can make them out of functions, we can make them out of permutations, we can make them out of matrices. Of course, matrices are just functions anyway. Okay, so there are multiple ways of making groups, okay? Okay, but the thing is that the whole point of groups is to be general, right? Is to say, here's the thing with letters, and if I have this thing with letters and it behaves this way, then no matter what this looks like, no matter whether it's numbers or symmetries or functions or permutations, I'll be able to know all this stuff about it because of the stuff I knew about groups in general. So I would like to know, even though this one is made of matrices and this one's made of permutations and this one's made of functions, are they really the same group fundamentally? Like they look different, but are they really the same? Like in terms of, if I drew a map of where everything went, if I just fiddled with it, like, because I can draw it on the paper however I want, if I just move things around, would it really be the same structure? And that's what isomorphism is about. Okay, it's about trying to tell if groups are the same. Okay, so groups will be the same if they're the same size. If they've got different numbers of elements, they can't possibly be the same. And also, if for every multiplication and result, there is a matching multiplication and result in the other one that works the same way. Okay, so that's the picture in my head, that's not the definition, but we've got everything matches, the sizes match, and if I label this one with this one, and this one with this one, and this one with this one, and then followed all the arrows, they would go to the same places. Okay, so one is just a relabeling of the other. Okay, so groups are the same. Relabeling one with the names of the other preserves the result, all the results of the operation. Okay? I mean, that's my words way of saying it, that's not the definition, but groups are the same if you just change the names and all the multiplication still works exactly the same way. I just change the names. That's what an isomorphism is. It's that relabeling, it's the changing of the names. Okay, and so what we have is, our relabeling is really just a function which sends one group to the other. That's my relabeling of the names. And I want doing the multiplication before with the old names to produce the same result if I do the multiplication after with the new names. Okay, so I want okay, well maybe this one's with a star and this one's with a circle. Okay, so this is doing the multiplication before with the old names. Whatever that produces the same answer as this. Sometimes it's easier to understand this statement here if it's written as this. Okay, that's another way of saying the same thing. If A star B comes out to C, then when I change the names, it still works. The new name of A, that's the new group operation. The new name of A under the new group operation with the new name of B produces the new name of C. Okay, so this is shorthand for this. But sometimes it's easier to think about it this way. But this is saying, this is an algebra thing, I can expand brackets, I can bring the phi in and the star becomes a circle. So that's doing it sort of on the fly. You're saying, well, I can expand brackets, but this is what's really happening. Okay. And it's only an isomorphism if it's one-to-one and onto. Okay? Because the two groups have to be the same size, they have to have the same number of elements. Okay, because it has to be a proper relabeling. Everything here has to appear here and vice versa. So one-to-one and onto function. Okay? Okay, so this is called phi is an isomorphism. So iso meaning same and morph meaning shape. So it's a thing, that's what an ism that produces the same shape. That's what. Okay. Yes.
Maintains the form.
That's right. Exactly. So there are other iso things elsewhere, we have isometrics, which preserve distances. And so yeah. So that's a maths word, iso something ism, will preserve something. Yeah. Okay, so the whole point of an isomorphism is just to notice that it's just a relabeling of the word, of the names. Sometimes it's difficult to come up with one bit. If it's not one-to-one and onto, so you can think about these things and say, well, just a second, if I wasn't aiming to try and relabel my groups to see if they were the same, and I was saying, I've got these things called groups, like the way I used to have things called numbers, and I used to have functions that went from numbers to numbers. Why can't I have functions that go from groups to groups? Which I could. And wouldn't it be cool if the functions that went from groups to groups tended to preserve, were able to be expanded out over the group operation? And so just focusing on just this bit of it, just that bit there, and not the one-to-one and onto, is called a homomorphism. Homo also means same, iso means precisely the same. Yes. So homo means same, but iso means exactly the same. Yes. So that's a maths thing, right? Saying, wouldn't it be cool if I could expand my function out over the group operation? What would happen then? And that's what homomorphism is about. Isomorphism is saying, wouldn't it be nice if I could relabel the names and it would turn into something that I recognised? Okay, so they're the same. They come from different places in terms of what we were aiming to achieve, but they're the same idea in the end. And there you go. That's my Zen meta level, right? And we get into. So if you do maths on maths like that, it's called category theory, which is cool and terrifying. Awesome in the sense of, cower brief mortal. Isomorphisms are hard to come up with. But what you need to come up with is a homomorphism first and hope that it's one-to-one.
Yeah.
That's one way of dealing with it. So there's a classic, the classic example is like, find an isomorphism that goes from R plus to R star. No. Something like that. Well, what you need is a function that turns plus into times. Okay, cool, I know one of those, it's ln. And that's to do with that, and that really is like one of those horrifying problems where the answer is, well, surely you remember that there was this connection that you should have seen so far. I mean, and a lot of them are like that. But we can just investigate what's supposed to happen. So we know that phi of A plus B is supposed to be phi of A times phi of B. This isn't ln, this is like e to the power of, actually. So we want something that when it's plus on the inside is times on the outside. And I need to think of all of the functions that I can think of, because it's really just a function that goes between R and R that only produces positive numbers out. And plus inside is times outside, and there are very few functions that do that. And I can't give you any better advice than that, except that there is a few other things that you can know. You know that the identity before has to be the identity after. Phi of 0 has to be 1. Because the identity here is 0 and the identity here is 1. So it preserves identity. And it also preserves inverses too, because it preserves the entire group structure. So I also know that phi of minus A will be 1 over A. Because that's A inverse, right? Because inverses here are negatives and inverses here are inverses. So and you could start creating a list, therefore, of things that must happen. So you could actually start going, all right, phi of 1 plus 1 would be phi of 2, right? But it should also be Is that right? So phi of 2 is phi of 1 times phi of 1. So it looks like phi of 2 is phi of 1 squared. So I'm just starting and saying I've got specific numbers, I'm going to see what happens to them. What happens to 2? Well, 2 is 1 plus 1, right? And 1 plus 1 would go to 1 times 1 because plus becomes times. So 5, 2 is 5, 1 squared. And actually, if I started thinking that way just a second, the 2 is here. The 2 in here became a power. Ah, maybe it's powers of something. And that would help me to think of what's going on.
So I'm just about to ask, so as a general group, all the powers.
The powers of
be a homomorphism.
Yeah, so the powers of any number, be it E or 2 or, well, positive number, is an isomorphism between R plus and R times. It's a different isomorphism. The labelling is different. But infinite groups are really confusing because you can label things differently and still get the same answer.
Yeah. 5 to the 3 plus 4 equals 5 to the 3 times 5.
That's right.
Yeah.
So the thing is that 2Z is different to Z, but 2R is the same as R. So, okay, so because every number has something that it's half of and 2 of, whereas that's not necessarily true in Z. Like not every number is 2 of something. 1, for example. Not in Z anyway. So coming up with homomorphisms, with isomorphisms is, I say, if you don't automatically think of what it must be, start investigating what it does to the identity, what it does to particular numbers. Okay, so you say, well, if I start with 1 here and see what it becomes, well, it has to be, squared, okay, 2 becomes a power. If I did that with 3, that had happened too. So everything's becoming a power. Okay, it must be a power of something. And then you could just label this with a new name. Okay, so, and the other one is if you're showing that things aren't isomorphic, is usually in the sense of saying, well, what if it was, and hopefully coming to something that's crap. Okay, so we know that R plus is not isomorphic to R star times, as opposed to just the positive numbers. And the way to do that is to say, well, what would happen if it was? And in fact, we know, based on this same argument here, that all this same stuff would have to happen. Because plus has to become times, right? And so it's actually going to have to be that phi of all the integers is going to have to be a power of that integer. And I'm actually going to, so I've got a feeling as to what's going on. I'm not going to be able to actually produce any of the negative numbers. And if I do, I'm going to have crap going on. So I should see what happens if I was able to produce -1 as an answer. So that's a way of thinking it through. And remember that isomorphism works both ways. So if I haven't been told which direction the isomorphism has to go, I can go this way if I prefer. So do the isomorphism that way, because that's a little easier to think about. Because I want to say, well, just a second, I want to show that -1 can't, if I go this way, there was nothing that's able to produce -1. What if I start at -1 and show that it couldn't produce anything that way? So phi of -1 it has to preserve inverses, and so this would be the inverse of -1 over here, which would be 1. But phi of 0 is 1 because it preserves inverses, so it preserves the identity. So that's preserve inverses, but phi of 0 is 1 since it preserves identity, and so it's not 1 to 1 because I've got two things that produce the same answer. Yeah. I'm not sure if you're allowed to use the preserve inverse and preserve identity rules. Pretty sure you can.
Well, you can. We just have to say it's not injective or whatever, whichever one it is, or surjective.
Well, technically, the isomorphism doesn't directly do this rule, but you are allowed to. There's rules in the book that say that phi of something inverse is phi of something. You can bring the inverse out. So. Yeah, so it can't possibly be because it doesn't preserve that. Yes?
What happens in questions where we've gone from like R2 general linear groups
Yeah.
or the other way around, is it perfectly valid to say if your general linear group has matrices of this form, that your isomorphism is that you just, that in real numbers it would just be a particular element in that matrix?
Yeah, your function is, so you're saying, your function is pick the 1, 1 entry of this matrix. Yep, that's okay.
Valid?
Yep. Okay, so your function doesn't have to look like a formula. It can just look like a input-output thing. Okay, because if we've learned anything about functions and about all of these things, nothing has to look like a formula anymore. I'm allowed to just go, I just define multiplication to be this list of possibilities. Okay, so by my Cayley table. Okay, so we don't have to define functions as formulas. We can just say, well, it's the 1, 1 entry of this matrix. That's my function.
That Simon question, 1, 1, 0, n.
Yeah.
And we can create the real numbers from that.
Yeah. And you can actually make the complex numbers from the real number using complex numbers from R2 using matrices and So, but investigating what happens for the basic things, what must happen, is really useful. And you know that, and knowing that the identities match up is a really useful place to start. So if I'm going to go R plus into matrices under multiplication, then 0 has to become the identity matrix. So knowing what the two identities are in the two things and what the inverses, how they match up, allows you to have a better chance of creating what you want. But you really need to try and preserve structure. You want to say, is there a way, if you wanted to turn, because there was a subgroup of matrices that is the same as the real numbers under addition.
Yeah.
And so you say, well, I've got my matrices, I need to have and I know it's not all the matrices, so I can pick whichever ones I want. And I need matrices that when I multiply them, it's tantamount to adding something. And the thing is that all of this is based, the reason why you have to do Maths 1A and Maths 1B first is so that something that you once heard once may possibly spark. Because you go, just a second, I know that if I multiply matrices that do row operations, it's the same as doing the row operations one after the other, and I've got row operations that do addition, sweet. Okay, so, yeah, and I know that matrix multiplication includes an addition in it, so if I can just make sure that I don't get multiplication wrapped up, I'll be, together, it'll be cool. So, yeah, and it really is like divine inspiration, some of these, and I hate to say that, but it really is sometimes. But as a good start, you can get a mark by saying, well, it must preserve the identity, so I know whatever it does, it must turn this into this. So at least you can make a start. So, subgroup. What's the name of the matrices of invertible matrices?
It's
GL?
GL.
2R or is it
3,
R2?
R.
Yeah. I can never remember what order they're going. Under plus. And this is under matrix multiplication. And so going, well, just a second, I do know that if I've got an isomorphism that goes from GL to R into R, I need to preserve identity, so I know that must happen because it preserves identities. And that would at least be something that was worth, maybe if it was if they had to find something that made the difference between pass and fail or credit and distinction, and they found that, they'd go, cool, bump them over, right? So it's better to write something than nothing. And so you can say, well, 5. Okay, well, it's a good start, right? I know that I have to be able to, this 0 must be constructed somehow out of that matrix. So I could conceivably pick one of the entries, maybe, or subtract something. So there's some sort of thing that on those 4 numbers that produces this outcome, and at least it's a start. Okay, because it preserves the identities, and then you go, well, it preserves inverses, and so you could say, well, 5, but you'd have to make a guess. So if I had whichever matrix produces 1, then I'd have, so if 5A equals 1, right, then 5A inverse would have to be -1 because it preserves inverses. And so that's really useful because I'm going to go, well, I need to find a way of somehow putting a 1 in here so that when I do the inverse matrix it produces a -1. And that's not very helpful, but it's a start. Yeah. So at least it's a start. You can, knowing that it preserves all the group structure. And you see what I did? It's the same as checking if something's really a subgroup or really a group. Start with the identity, then do inverses, then do the group operation. Yeah. Because you start with the thing that's the easiest to think of first. It's the same as when we did subspaces. To check that something's a subspace, you should start with non-empty, then go to scalar multiplication, and then go to addition, because scalar multiplication only needs 1 vector, whereas addition needs 2. So even though traditionally scalar multiplication is listed as the second rule, it's really, in terms of what you should have tried to check first, the first rule, because it's simpler to check than it is to check for addition. So it's the same deal. Inverses are listed as the third rule, but they're easier to check than all of the multiplications. Yeah. All right, that's probably quite enough for today. I'll just mention cosets. So, I want this to last for a while, this seminar. So, okay, so isomorphism was the first bit of group Zen. Okay, they look different, but they're really the same. Okay, so the next bit of group Zen is it's like meta groups. Okay, that's what cosets are about. So we're gonna take a group, we're gonna do this funky thing to it and make this new group so almost out of nothing. Okay, so right. Sorry.
So it seemed.
Yeah. Okay, and it really is magic. Okay, the cosets in groups are way more important over in vector spaces, because vector spaces are fundamentally a group first. Okay, because you need a group under addition, and then you do scalar multiplication, and you tack that on. Okay, so never forget that vector spaces are groups first, and then scalar multiplication. Even though you check the scalar multiplication first when you check if there really is a subspace. Because cosets will come back. Okay? So, cosets are similar to what you do in 3D geometry. If you take a plane through the origin and you add a vector to everything, it'll shift up to a different spot. Okay? That's a coset. That's what a coset is. Okay? So, I'm going to draw my group blob diagram.
So it's a scalar.
No, it's an addition. Okay, so cosets make.
Oh, sorry.
Yeah. So my blob diagram of my group elements, and then within my group I have a subgroup somewhere. So I've got all my group elements, and I've got my identity down here, and including the identity, there's a subgroup of some kind, right? Okay, so this is my subgroup. So that's my group. Okay. Remember what I said about, in my second diagram right at the beginning, I said about how instead of thinking of a group as taking pairs and producing an output, I can think of it as having a separate function for every group element. Say, well, I've got this group element number 1, and I could add 1 to everything, what does that do? And I've got the group element number 2, I could add 2 to everything, what does that do? So every group element has its own function that says what that group element does to all the other group elements. That's what cosets are about, okay? I know that if I just took a single group element from anywhere, I could multiply everything in the group by that group element. and they would all end up somewhere. Okay? Right. So I could times this one by G, and 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 I would produce another little collection of group elements. Well, that collection of group elements is the coset that G made from H. And so G, H. I took all the elements of H, multiplied them all by G, and I managed to shift the subgroup over to here. It's not a subgroup anymore because it doesn't have the identity in it, but it's the same sort of shape. Okay? I just moved it to a different spot by multiplying by G.
That'd be like moving a parabola up.
Exactly like moving a parabola up. Okay? Only with the parabola it's addition, not multiplication. Okay, so cosets makes more sense in geometry as addition rather than multiplication, which is why one of the reasons why it's confusing. Makes much more sense as plus. Okay, and then if I took a different group element, I might make a different coset. Maybe I'll times this one by K, and I'll make this coset here. Okay? And what will happen is you'll be able to cut the group into pieces, and each piece is a coset. And the magic of groups, of the way that groups work, is that if I multiply everything in here by G, it might be that there's some other group element that I could multiply everything in here and produce the same thing that I get here. Okay, so maybe there's another group element that everything's in a different order, the arrows are going to different spots, but it produces the same thing overall. Just blow that up so that it's easier to see. So maybe, there's my identity, maybe when I times by G, I get that. But maybe if instead I times by something else, P. I end up with the same collection of dots overall. I know that the screen can't see the difference between the blue and the black very well, I'm sorry. Okay, so I could times everything by G and end up with this set of dots. I could times everything by P and I get them in a different order, but I get the same collection of dots. And so what I end up with is that this coset, which was GH, is also PH. Sorry? They're not distinct. Because as a collection of elements, they are the same collection. Because remember that GH is a set.
Yeah, but like GH and KH are both very distinct cosets.
Yeah, GH and KH are different.
Yeah.
Okay, so that's the first magic of subgroups, okay? That every coset, you're not going to have cosets overlapping like here. There's not going to be a coset like that. They're all going to cut the group into slices. Okay, so the picture in my head is that this group gets copied, the subgroup gets copied, and the big group is cut into slices. And no matter what you multiply this whole group by, the collection in total of the dots that you end up with ends up being one of these slices. Yeah?
So there's never an intersection?
No. The cosets are disjoint. Okay, so the cosets taken as just the collection of possible sets that you could possibly produce are disjoint. But if you think about the coset as multiplying by G or multiplying by P, you might end up with the same coset. What they don't do is overlap a little bit. They either have to be fully on top of each other or fully separate. Okay?
So it's sort of like the partition of a set when you have all
They are precisely a partition of a set. That's one of the reasons you talk about partitions at the beginning.
Yeah.
So what we're now going to do is, instead of thinking about instead of thinking about the subgroup, the G acting on each element of H separately, I'm going to think about G acting on the whole subgroup as a blob. Right? So this would be times G, right? And it was also times P. And this was times K. Okay, so the various different elements of the big group, I multiply them all by H, I'll produce various different cosets. But there will be one, every element will produce one of these 4 cosets, or however many there are. Okay? So, the magic of groups is, if you get a subgroup and multiply it by one of the group elements, you will produce another slice of the group, which you'll either produce the same bit again, or it will be a different slice. Okay, so sometimes if you multiply by something, it might end up here, right? It might end up, times it by Q might end up at the same spot. So this subgroup, it's either going to multiply everything in the subgroup by something, and I end up here, or maybe I end up there, or maybe I end up there. But what you will end up is in one of these slices. So that's why Lagrange's theorem works, because of of cosets. It says, look, if I multiply everything in my group, or add, or whatever it is, I'll produce a separate slice, and those separate slices add up to the whole group. And they're all the same size, because there were 4 elements here, and I multiplied them all by something, and it produced another 4 elements. And so that means that I've cut the group into slices of size 4, so 4 must go into the size of the group. So that's what cosets are about. And what we start to do is say, just a second, let's think about it. We've been thinking about things that look different but aren't before. We've seen that rotating my pentagon 6 times is the same as rotating it once. But we've now got that again, haven't we? We thought it was different. When we look at the individual group elements, timesing by G has a different effect than timesing by P, because everything goes to a different spot. But when I just look at the whole subgroup, as a whole, the whole subgroup's in the same place. So we thought it was different, but it's not. And every time you see that, suddenly there's an opportunity to make a new group. Okay? I had all possible numbers from 1 to, from minus infinity to plus infinity for rotating my pentagon. As it turns out, 6 is the same as 1 and it's the same as minus 1. It's like, right? So, same deal. I had all these possibilities for timesing my subgroup by something, but actually, timesing by G is the same as timesing by P. Because I'm not looking at the individual elements anymore, I'm looking at the whole group. So any time when something happens the same, even though it looks different to begin with, we've got an opportunity to make a new group. And so we're going to make a new group, and we're going to say that timesing by G, timesing this subgroup by G is the same as timesing this subgroup by P, so G and P are the same in this context. Okay? So we just need to now say, well, it's only a group if we can multiply those new things by each other. So presumably, taking H and multiplying it by G and then multiplying it by Q, right, should be the same as that. Timesing out what QG is first and then multiplying that result by H. We're hoping that it comes to the same answer, which it does. So sweet, we can now define a new group. Okay, so we talk about representatives of cosets and whatever, but we're just doing the same thing that we used to do when we said 6 rotations is the same as 1. Okay, we're now just saying, well, just a second, timesing H by G is the same as timesing H by P. I don't care, I can use it whichever one I want, it'll always work fine. And I know that even if I had 6, 6 plus 4 will come out to the same spot on my pentagon as 1 plus 4. Okay, so I don't need to worry about, because I proved, you have to prove it, but I proved that I don't need to worry about which of these numbers I pick and just pretend it's the right one. Yep.
Weird analogy, but it's like mixing paint. You don't have to drive around with every single colour.
No.
Because you can have your base colours, mix it to what you want.
Exactly. So the analogy we have here is that it's like mixing paint. You don't need every colour, you just need a few of them. So I don't need to know what P does to H, because all I need to know is what G does to H and the fact that it's the same. Okay, and I don't need to know, this might be green. I could achieve that by first doing yellow and then doing blue, and that'll be okay. Okay, so, right. So that means that we can now create a brand new group, and it has less things in it than the old group used to have. Because timesing by P is the same as timesing by G, so I've got less things overall. And I used to have a 6 and a 1, and now I've only got 1. So my group suddenly wraps around again. The way, because I'm not looking at the individual elements, I'm looking at whole subgroups, pieces of the group, cut it into slices. So that's the picture that's in my head. And the picture that's in my head really is actually in 3D where it's plus. So if you take maybe R2, maybe not R3, R2 under plus, so 2 vectors with 2 coordinates under addition, I can make subgroups, which would be subspaces. Okay, that's the line y equals x, which is a subgroup of that. Okay? So, the collection of k times 1, 1. Okay? That's a subgroup of R2 under plus. If I add any 2 vectors on this line, I remain inside the line. It's self-contained in the group sense. But then what I could do is I could make cosets out of it, right? I could add 1, 0 to this. So I could add 1, 0 to every single point on that line and make a coset. Okay, so this is my line. My coset is 1, 0 plus my line. And that produces this entire line here. And that's not a subgroup anymore, because it doesn't go through the origin. It doesn't have the 0 vector in it. There's no identity. Right? But I could just as easily have produced that coset by shifting this way. It's the same. Sorry, that was 0, 1, by the way. Could just as easily have done that and produced precisely the same line. Like I could have added minus 1, 0 to everything. Okay, so these two, while I thought I was doing a different operation, overall it produces the same line. So these two cosets, which I thought were different, are actually the same. Okay? And the key point is that if I want to think about where the lines go, I don't have to find the whole line first. I can just find out where the individual vectors go. If I wanted to get to, say, here, I could go up here and then up that many. So I could actually move the whole line and then move the whole line again. Or, if I wanted, even better, I could just move this and then move this and then add that resulting vector to the line. Okay? Right, so let's just think. I could add everything in one set to everything in the other. No, it's okay. Let's forget that. Yeah, so I could take a coset and then add 1, 0 to everything in the coset and add, 2, 0, 2 to everything in the coset and end up there. But I could just as easily just added 0, 3 to the original one, and it all works out okay. So addition here, addition of lines is the same as just addition of individual vectors. Yeah, but when you break lines like that and shift lines up and down, what you're really doing is making cosets. Yeah. And so the way that those lines are related to each other in terms of how far apart they are is the same as how the real numbers are related to each other along this y-axis. And so we have a new group, but it's the same group as one we knew already. So we can say that R2, right, factoring out this line,
Oh, that's called
well, it's factor because it's division.
yeah.
This is the factor group. R2 is the big group of all the vectors and how they add to each other, right? But if I have a single line and I focus my attention on the line and what it does, well, the line has the same structure as R1. Because I can move it up and down, right? So that's isomorphic to just R. So that's the idea of factor groups, is to say, well, just a second, if I have my subgroup, I make copies of my subgroup using the group elements, and then I forget that I had individual group elements and just look at the sets that I made, they have a group structure as well, which is the same as what I always do when I make groups, which is forgetting some of the structure. What structure does it have? And that's what this factor, this division sign is about. Right, and then isomorphisms come in and there's all this other stuff. But that, at the very least, I can at least have given you my picture of cosets, which is lines.
It's a hell of a lot easier than imagining a 1 3 on the square.
Go one page back to the potato. Yeah. So I didn't want to interrupt before and then drop the word isomorphism. That's not to confuse the issue, but is a P, so a little bit lower down, P and G.
Yeah.
Are those operations isomorphic? Or am I just confusing the issue by bringing up the word?
Yeah, isomorphism doesn't really
Okay.
match in that point.
Alright, we'll leave it there then, yeah.
You're right, they produce the same result though.
Yeah.
Overall, they don't produce the same result on the individual elements because they all go to different spots. But as on the subgroup as a whole, it produces the same result.
So the same boundary.
Yeah. Yes. And in the end, cosets usually just have to go, right, I have a picture, but then I also have this list of things that I can and can't do that I'm just going to deal with on the algebra on the paper. Because sometimes you can't marry your pictures together, but I do really... Cosets make a lot more sense under addition than they do under multiplication.
Yeah, I never understood the coset with the square multiplying it by a flip. I just did not get that ever. That I get.
This is really cool.
Yeah.
And the fact that they don't intersect,
Yeah.
which means I've made a mistake on that.
Yeah.
So with your square, the symmetries of a square, where'd my text to go? You could make the subgroup of rotations, for example,
Yeah.
of which there are 4, right? And then the rest of the group, and we haven't covered the whole group. So there's 8 elements here in total, right? And we know that the whole group is split into pieces that are the same size as this subgroup. So I've got a subgroup of size 4, which is the rotations, and another bit, which is also size 4. That must be a coset. Okay, and what it must be is a rotation times something else. Okay, so I know that this rotation times a flip. Oops. Forget that I have to draw it on the back as well. If I was really clever, I'd do it on clear plastic. But a rotation times a flip is not a rotation. I can't get to this by rotating at all. Okay? And so the thing is, if I take each of my rotations, that's my first rotation, and then a flip, which produces that. And then I have my second rotation and the same flip, which produces that. And then my third rotation and the same flip. What it'll make is 4 different symmetries. And those 4 different symmetries cover the rest of the group.
Could you represent 2 flips in a rotation?
Sorry?
So if you do an H and a V, could you then represent that in some sort of rotation?
Yeah, that's right. So the idea is that if I took all the rotations and then did a H and a V, it would come out as one of the rotations again. And so H time, an H and a V.
These numbers aren't backwards anymore.
Yeah, but in terms of cosets, the coset of rotations, coset of rotations times H and the coset of rotations times V, I multiply them together, gives me the coset, the original set of rotations. Okay, so I'm starting to see the cosets as objects in their own right. So the whole collection of rotations and all the other ones are two objects in their own right. So as I said, I've made a group out of nowhere.
Yeah.
Okay, I had a group to start with, and I went, I've got a subgroup. Slice it up. Ta-da! I've got a new group. Yay! Okay, so I sort of made this group out of nowhere.
Just to be clear, so like I'm a bit behind on this one, right? And I'll catch up on it later.
Yeah.
But I'll try and word this right. What you haven't done, right, is you say you've got S4, and let's say this symmetries of the square is a subgroup of that.
Yeah.
When you're doing this coset viz, have you created all the other elements that are in S4 that are
No.
not in this? Okay, yeah. I
No.
thought, but I wanted to make sure that's
You've
not-
created something new that's entirely different.
Right. So it's
you-
still not a permutation of four numbers. So
No, it'll be a permutation of something else entirely.
got it. Right.
Because one has to be next to two.
The cosets are permutations of something else. They're permutations of the group.
Okay.
So this symmetries of the square is permutations of the numbers 1, 2, 3, 4.
Yes.
The group that I make, the factor group that I make out of the cosets of the rotations, the thing that it is permuting is the cosets.
Oh,
Because I think in D4, one has to be neighbouring to 4 and 2.
Yeah.
In cases where in S4 that's not the case.
That's not the case. But yeah, I'm not making something up in S4 because it doesn't. S4 is still
That's all right. I just wanted to
Yeah.
make sure that I didn't think of it that way.
S4 is still permutations of four things.
Yeah, that was just a donut for me.
But I only have, technically, I've got two cosets now, and I'm actually doing permutations of two things, the cosets. So what I'm making is S2.
Okay.
oh, because you've got two.
Okay, so over here, I have four cosets. The subgroup that I'm making out of the cosets is a subgroup of S4. Okay, before I had 16 elements, and so my group was a subgroup of S16. But now I have 4 elements, they are the cosets, and so it's going to be a subgroup of S4.
Because you're talking about the cosets, we're not worrying about the elements.
The elements are gone. The elements are gone, I rubbed them out.
Oh.
So can we think of that in the same way, like 2Z, 3Z, 4Z?
So,
It's all taking a slice
okay,
out
so
of the numbers.
yeah, and cosets are there as well. So 2Z is a subgroup of Z under plus,
Yeah,
and the rest of Z is the odd numbers, right?
yeah,
They are a coset.
yeah.
Okay, so I have Z is made out of 2Z, is made out of the even numbers and the odd numbers.
Oh, and they don't intersect.
And they don't intersect. They are a coset. So the and in fact,
And the only way you can arrange them is like.
in fact, Z5 is already made of cosets.
Because prime.
No, because of it's the equivalence classes. Like the 0 in Z5 is all the multiples of 5. Technically, that's what it really is. Z5 is already a factor group. So we've got Z.
I'm loving this group.
Okay, so I'll do Z3. Okay, so I have a subgroup of Z.
Yeah.
Crap. Might as well start a new page. I have a subgroup of Z. 1, 2, 3, 1, 2, 3, 1, 2, 3. Alright, so my black ones is 3z.
Yeah.
Okay? Now, if I take those numbers and I make a coset out of them, which means I add to those numbers, or add to every single one of those 1, right?
Yeah.
Then my purple that I have made is the coset 3z plus 1. And I could also just as easily do 3z plus 2, right?
Do you use a colour pen?
No, I'll just use orange. I know orange isn't the best. So I made 3 cosets. But I could just as easily have done 3z plus 4 and gotten to the same spot as the purple ones.
Yeah.
Okay? So this is just as easily, could just as easily have been 3z plus 4. Right? And this could just as easily have been bloody
No, dog,
frill.
again.
So I'm trying to relate that back to the idea of how many distinct cosets we have.
Okay, so 3z minus 1. Okay, so if we look at it, I'm only able to produce 3 distinct cosets.
Yeah.
The black ones, the purple ones, and the orange ones.
After
Okay.
that, they're only black.
Yeah. So even though they look different, 3z plus 1 and 3z plus 4, as I write them, they look different, but they're really the same as 3z plus 1.
Yeah.
Okay? And now I can do this magic trick, which says that this purple set plus this orange set gives me the black set.
Oh, yeah.
Because if I take any purple number and add any orange number to it, so here we have minus 2 plus 2, I get 0. Minus 2 plus 1, 2, 3, 4 plus 4 is 2, which is an orange number. So purple plus purple is orange. Okay? So, right? So no matter which representative I pick, it works. And so now instead of thinking about the individual dots, I can now think about the 3 coloured blobs. And you can go, orange plus purple is black.
So the blue set, green.
Yeah. And that's what I'm doing over here with this. I'm going to stop thinking about the elements, I'm just going to say this bit plus this bit is this bit. Okay? But what it does is it follows the structure of the group underneath. Okay, it's just that, well, orange plus purple is black because any individual orange number plus any individual purple number is another individual number in the black set. Okay? And this structure is the same as just using the numbers 0, 1 and 2.
Yeah.
Yeah.
Yeah, right.
Which is Z3.
Yeah.
So you've already seen a factor group. Okay, so remember when you were told that Z3 was really the 3 equivalence classes?
Yes.
Well, it's the 3 cosets.
Right.
You've seen cosets already. They were equivalence classes.
Right.
Okay, so we have here that Z3 is already Z factoring out 3Z. That's what it means. Okay, so we're now going to say, so in my head, you are seeing the whole group, subgroups and its cosets as the individual objects, but you're not really doing that. You're just saying, oh, you know, all the multiples of 3, they're the same, so I might as well just represent them all with 0. So I'm taking all these black sets and going, just a second, I'm going to replace this whole thing with a black dot and a purple dot and an orange dot. And I know that they wrap round Because if I just keep going that way, there's another black dot over here. Okay, so I'm saying that this black dot is now representing all those black dots. And this purple dot is now representing all those purple dots. And this orange dot is now representing all those orange dots. So I had Z and 3Z. And then out of 3Z I constructed two other sets. And then instead of looking at the whole sets, I just picked a dot from each of them and said, now I've got a new group. That's what cosets and factor groups are all about. So you've seen factor groups already. So do you know what I said? Any time when you say, oh, they look different, but I'm going to declare them to be equal, I declare 4 to be the same as 1. Any time you're doing that, you're already making cosets. And you're already making factor groups. Okay.
I'll run out of light bulbs to switch on.
Hopefully you'll watch it again another day.
That escalated quickly.
That will do for now. I'm going to stop the recording.